This video summarizes the article Step Counting on Smartphones Using Advanced Zero Crossing and Linear Regression by Jungryul Seo, Yutsai CHIANG, Teemu H, LAINE, and Adil M. The article was published on IMCOM 15 Proceedings of the 9th International Conference on Ubiquitous Information Management and Communication with the article number 106. The journal itself is published on January 8, 2015 by ACM New York, New York, USA. 3 researchers from South Korea, and 1 from Russia, has proposed a design and implementation of a step-counting algorithm for Android-based smartphones, which is both battery-friendly and, to some extent, subject-independent, using advanced zero-crossing scheme and linear regression to estimate the number of steps taken by the user. The first step is to get the data from the phone's accelerometer. But wait, what is an accelerometer? And what data does it produce? An accelerometer is a built-in device that measures the acceleration of the phone on the 3 axes, X, Y, and Z. After acceleration data is obtained, a noise reduction is applied to the raw data. Well, not that kind of noise, but unwanted modifications of the signal throughout the process. Then, the walking detection module processes the noise-reduced acceleration data to detect if the user is walking. It is done by first analyzing the SMA, or signal magnitude area, of the 3-axis acceleration signal, which is obtained by this formula, where XA, YA and ZA indicate the acceleration signal points along X-axis, Y-axis and Z-axis, respectively. If the SMA value is greater than a certain threshold value, the user is walking. And finally, if the user is not walking, the system goes back to reading the next batch of acceleration data. Else, it will proceed to the important step, which is step counting. Later, when the user stops walking, the produced step data will be stored and the system returns to fetching the acceleration data. So, what steps are involved in the step counting? The first one is called advanced zero crossing. A zero crossing is an event where the acceleration of a certain axis, for example the y-axis, passes through the zero mark while propagating over time from positive value to negative value, or vice versa. However, even after using the noise reduction technique, the acceleration signal still contains some noise which can make the signal register zero crossing even when the user is at rest. To solve this problem, advanced zero crossing method is used. It is achieved by using artificial boundaries on both sides of the 0 point named a DZC range, which is calculated by this formula. Both the constant and standard deviation are obtained through examination. Zero crossing is considered only if the signal has come from outside this range, otherwise it is ignored. The last step is the linear regression. What it does is mapping the number of zero crossings to the number of steps taken, by using a linear function that represents the correlation between them. Okay, we currently have the number of zero crossings, but how does the system know the number of steps done by the user? The answer is by training the system, which is giving a set of known number of steps for the system to process. To illustrate this, let's use an example. Say, the user is asked to step 5 times, then step 10 times, then stop, and so on. These number of steps are already programmed in the system. Therefore, a number of plots can be obtained to produce a linear function, such that given a random number of zero crossings, the system can estimate the number of steps taken by the user. Mission accomplished. Well, not really. There are still some issues that occur. Firstly, during the tests, subject-dependent test shows an average of 90.63% accuracy, while subject-independent test shows an average of 89.07%. What it means by subject-independent test here is to train the system using data from 2 people and use it on a different person. It is quite impressive. However, the problem is in the range of accuracy. For subject-independent test, the range is 85.11% to 91.09%, which means the result fluctuates quite a lot. The algorithm is also position-dependent. The system is tested only for pen's front pockets. On the positive side, the test shows that without the app, the power consumption is 205.37 mWh, while with the app running, the power consumption only rises to 233.07 mWh. However, given some issues stated before, the 4 researchers have some works to do to improve the algorithm before it can be utilized for public use. This video is brought to you by Andrew Putra Kusuma, undergraduate student from School of Computer Engineering, Nanyang Technological University. Thank you for watching.